Okay, so just now we talk about MTTF and MTTR. Okay, MTTF and MTTR in the sense of reliability, in the sense of probability, right? We can calculate the reliability of a series system, and we can calculate the reliability of a parallel system. So what if we don't analyze the system in terms of probability, but rather analyze the system in terms of failure rate and also repair rate? So this is how we do it, right? So if you have a component in series, okay, you have a component in series, then we can describe the probability of the up state as such, mu divided by lambda plus mu. So how do you look at this is that from the up, let's say this is up and this is down, from up to down, then the rate of that happening is described by the lambda failure rate. Then from down to up, it is described by the repair rate mu. So you want to, because you are flowing, you want to calculate probability of the up state. So you take the tendency of going to the up state, which is described by mu, divided by the total of the failure rate of the rates. So the rate will be failure and the repair rate sum up together, and that will give you P up. And then from the series system, we know that the total failure rate of the system is the summations of the failure rate from component 1 and component from state 1 and also from state 2. The failure rate of the system is given to us as the summations of the failure rate by component 1 and component 2, okay, given to us by this equation. So these are the characteristics of a series system. So for parallel is the opposite. The probability of in the down state is given to us as this, and then the repair rate of the parallel component is given to us by mu1 plus mu2. The repair rate of the first component plus the repair rate of the second component will give us the repair rate of the entire system, right? All these are just general reliability concept, and we have not even gone into power system reliability yet. And it's a bit too complicated, right, to describe what power system reliability is into one lecture series. But I can share with you with one concept called Monte Carlo simulation. So Monte Carlo simulations, I have to deviate a little bit from these lectures to talk about Monte Carlo simulation. But it is a very powerful tool that power system engineer often employs to analyze the reliability of the power system. So what Monte Carlo simulation does is that it basically simulates the random failures of power system components. So the random failures of these power system components are described by the failure rate, repair rate that we just talked about, right? So these are just concepts for you. So when we simulate the random failures of this component, then we take all these random simulated component at all the time interval, okay, at all the time interval into our consideration, and we calculate we calculate a certain mathematic process, which is what we call the power flow. I believe this you have learned in power system analysis course, right? So we take all these components, their status, we consider all them, and then we consider their status and their functioning and their impact in our power flow. So from the power flow, we extract the information that we want. So one of the information that we can extract is called psi phi over here. Okay, and many other more information later on from this lecture series. So the question is why we want to go through all these troubles of simulating components, their random statuses. It seems like a lot of trouble. Why not just use hand calculation, right? The reason is because power system components is very large in number. Just think about it, right? This is a simple probability discussion. If you have two components and each of the component can be in the up and down state, then you would have four possible states. Meaning that the formula to do that will be 2 to the power of 2. Okay? And just consider now, if you have 10 components and each of the component can be either in the up or down state, then the number of possible state now